Hello and welcome to this week's Preparing for the PAT session. My name is Kat. I'm the Physics Access Officer at Oxford University. My pronouns are she, her. A few ground rules for this evening. Those of you who are joining us on Zoom, hello, you are welcome to join us with the chat and the Q&A. Those of you who are joining us on YouTube, hello, you won't be able to join in with our chat and Q&A, but you will be able to watch along later. Those of you, who are using the Q&A and the chat, please make sure that you are polite, you are friendly, and you don't share any personal details in the chat. If at any point you are feeling unhappy or unsafe, do feel free to get in touch with the host and panelists, and we'll put you through to our safeguarding screen. But without further ado, I'm going to talk you through the PAT test and PAT prep course. Give you a very quick introduction to these two things before we move on for today. So first things first, the PAT is the physics admissions test. It is the required test for physics, physics and philosophy, engineering and materials science. That means it is a test which must be sat by all candidates applying to those subjects. Your result on the PAT forms part of the information for the admissions tutors to use, and they use it to decide who to shortlist for interview alongside all of the other information on your application. In order to sit the PAT, you will need to register yourself as a candidate. Your school will not do this for you. So it is your responsibility to get registered for the PAT. We'll take you through a little bit. This year's PAT, October 2024, the format is a little bit different to previous years. The PAT is going to be on screen and multiple choice. Although this is a change of format, the syllabus is completely unchanged and nothing else has changed about the PAT. So don't worry too much about it. That syllabus that I mentioned is online, and it is your responsibility to cover that syllabus by doing individual learning as needed. We'll give you some hints and tips. And in fact, I share some hints and tips in the emails that come round. So that is the PAT itself. What about the PAT prep course? Now, the PAT prep course is a series of 8 webinars, and I run this course on behalf of all of those subjects who require the PAT. We are currently on webinar 6, and it's worth pointing out that this PAT prep course is designed for people who are sitting the PAT this academic year. So people who were in year 12 when the course started in June, you may not have joined in June, don't worry. Welcome to anyone who's new, and who will be sitting the PAT in October 2024, aiming for either entry next October or applying for deferred entry for the following October. If you are not in that position, if you are a lovely new year 12, or even if you're a little bit younger, this course isn't really one where there's a benefit to starting it early. Your best bet is instead to follow our amazing year 12 program. So we have a program of taster mornings and masterclasses, all of which build up your knowledge about applying to Oxford and other competitive universities and put you in a great place to join our Preparing for the PAT 2025 course, which will start in June 2025. It feels like a really long way away, but it will be here before we know it. On screen, you can see our timetable for the PAT prep course. This is attached to every email that I send. It's always highlighted in yellow so that you know where we are. All of the materials that we use in the course are available on our course material page. There's a little sample of that on screen now. At the top, we have an introduction to physics problem solving, how to be a physicist. This was our study focus 1, which we did way back in June. But there's also some extra information in there. And if you didn't manage to make it to that webinar, do not worry, because down at the bottom, the recordings of all of our webinars, along with the problems that were used and the problems which were to be solved later, are all available, along with our summer assignments and links to our problem solving YouTube channel. So at any point, you can access this whole course and get going. Some practical information for you about the PAT before we jump into our session. The most important link for you to have is the one which is currently on screen. I share this in every email that I send, and this is the link that has all of your information that you need in order to register, all of your syllabus information, links out to FAQ pages, how to register, all of that information is found at that link. It's the most up-to-date, and it's the one we recommend you check in with regularly. The PAT this year will be sat at a Pearson Test Centre. These are all around the world. They are an international organisation. Pearson are also responsible for administering the LMAT, the BMAT, the Cambridge admissions test, and all manner of tests sat all around the world. So all candidates will sit the test, the PAT, at a Pearson Test Centre. Registration for the PAT is already open, and it is open until the 4th of October. I highly recommend, if you are planning on sitting the PAT, you get yourself registered as soon as possible. For most people, the registration process has been really smooth, but in the unlikely case that you run into some trouble, try and build in some extra space for yourself to make sure that you have enough time to get in touch with us and to sort any of those problems out. When you register for the PAT, if you require access arrangements, if you need something like extra time, if you need extra breaks, you must apply for those access arrangements when you register for the test. Can't go back and do it later. So make sure you tick the correct box and follow the process. Everything that you need is detailed in the how to register page. There's a big read this first document, and I recommend you do that. You can also watch the webinar from last week, because last week what I focused on was the practicalities of registering for the PAT and exam technique. So do take a look back at that webinar. The PAT is on the 28th of October. This is a Monday. For some of you, it will be in half term. You can sit the PAT anywhere that you wish. So if you are planning to be away, you can look at that. That is the date of our PAT. And there is a practice test along with an on-screen calculator, which is available from that website too. Hopefully that has covered everything that you need for the PAT. That was our quick introduction. I give that every single week. What I'm going to do now is hand over to two of our lovely students. I have a current undergraduate and a lovely student who is between her master's and PhD. They're both joining us today. They're going to introduce themselves and they're going to take you through problem set 3. I'm going to be in the background. I'm going to switch my microphone off. I'm going to be manning Q&A and the chat while they take you through your solutions. So any questions that you have, either about the problems, which Aggie and Hiron are running through, or more generally about the PAT, pop them in the Q&A and we will be happy to help you. But over to you. Who's going first? Is it you, Hiron?
It's me. I do the odd ones.
I couldn't remember who was
so I'll
doing
go
odd
through
numbers.
first. Yes, I'm the
Hello,
one
Aggie.
that's stuck in. Hello, I'm the one that's stuck between two courses, both at Oxford. So I'm still staying loyal, not going to the other place, Cambridge. Anyways, right. So I thought, given that we have 8 questions and they're quite long, I'm gonna give a overview of how the question is how it works, but like any details which are not like, because these questions focus on circular motion, so if there's an element which focuses on the suva, I won't go through that, just to kind of save time, and if someone wants me to go over it, then put it in the chat and I will go over it. Right, so let me share my iPad screen. I never remember how to. Oh, okay, there we go. The Zoom changed the settings. Okay, right. So can you now see my iPad screen?
I can see that you've started screen share. Oh, there we are. It's just being a bit slow to come through.
Oh, okay, good.
Yep,
right.
Good. I can see you now.
Nice. Okay, right. So we're going to start with question 1, which describes, so it says, a smooth marble is initially at rest at the top of a much larger hemisphere of radius r. The marble is given a slight nudge and begins to slide down the hemisphere. And then, okay, well, I kind of just drew the diagram of what it looks like, and this is going to be r. This is going to be r, because in a circle, obviously, the radius is the same everywhere. And then the first question asks, at what angle from the vertical will the marble leave the surface of the hemisphere? So let's again kind of put all the angles in. So it talks about the angle from the vertical, like this. And then we have this to be theta. If, for some reason in the PAT you thought that the angle would be here at the bottom and not at the top, and you work that one out, then obviously you probably lose like 1 mark. So no stress if you don't know exactly what angle they mean. But anyways, so this problem, clearly we have a circle or a hemisphere, but we slice it into a plane, which is basically half a circle. And let's see what we have to do. So at what angle from the vertical will the marble leave the surface of the hemisphere? So let's kind of resolve our forces first. So we're gonna have the reaction force pointing along the radius, because remember the reaction force always acts perpendicular to the surface. And then we have the weight, which is just mg. So whatever kind of way you remember this method, but this line is perpendicular to this line. So in school we used to call them zangles, right? That angles where we have two parallel lines and you have a line between them. This angle, oops, sorry, this angle and this angle would be the same. So we called this kind of rule in school zangles, and then you have fangles, which is this angle and this angle are the same. But whatever you want to call it, these two angles are the same. So now, as we do with all these force problems, we can resolve our forces. But of course, there's no point about resolving our forces horizontally and vertically. It was going to be most useful to resolve them here perpendicular to the surface of the sphere at the point at which the ball leaves, and parallel. So let's do that. So, well, we don't really care about the parallel one, actually. So let's just resolve them along the direction perpendicular to the surface of the sphere. So we're going to have mg cos theta minus n is equal to mv squared over r. So let me just kind of explain this equation. On the right-hand side, I have the centripetal force, which is the force that an object experiences when moving in a circle. And then I have my two forces, the gravity and the natural reaction force on the left-hand side. Why is it not n minus mg cos theta? Well, that's because remember the centripetal force points towards the object, which means that my m times g, the component of m times g that I'm resolving here, is going to be also along it. So that's, the positive direction. And the natural reaction force is in the opposite direction. That's why it's a minus. So the condition for when an object leaves this hemisphere is that the natural reaction force is 0, because at that point it's not pushing down on the sphere. It's just think about it as you're about to lift off the ground, right? When you're just about to jump, at the moment that you're just about to lift off of the ground, you don't feel the ground on you at all, right? So let's just set n is equal to 0, so we can kind of write it in words, because that's how you should be displaying your problem. So when a marble leaves, n is equal to 0, right? So we have the equation mg cos theta is equal to mv squared over r. So we can just kind of divide by the mass straight away, just to not bother ourselves with it. So we're going to call this equation 1. And we want to find theta. So clearly we need another equation somewhere here. And a good way to go is, once we've resolved forces, is let's conserve energy. So right up here, let's call this position A, and we're going to call this position B. So at position A, because the marble is just nudged, is not going to have any velocity, which means that my energy at that point is going to be equal to just the gravitational potential energy. So mg times r, because that's the height above the ground. In the second point, now I do have some velocity, right, which I'm just going to call v. So my energy is a half mv squared, and now my distance above the ground is going to be this distance. Let me just maybe highlight it. So again, trigonometry, that you can use trigonometry to find that this distance is mg r cos theta. And of course, my energy is going to be conserved, which means that I need to equate these two equations. So I get mgr is equal to a half mv squared plus mgr cos theta. And let's divide this all by m and times it by, let's divide all of this by m times r, just to make our life easier, right? So the left-hand side, I get g is equal to v squared over 2r plus g cos theta, like so. Times everything by 2 and rearrange, so I get v squared over r is equal to something. So I get v squared over r is equal to 2g minus 2g cos theta. So now we have a second equation, and we can solve everything, that we've set out to solve. So let's substitute the first equation into the second equation, because as you notice, the reason why I kind of manipulated it in a weird way is so I could have a v squared over r here and a v squared over r here. So let's just substitute that in. So we get g cos theta is equal to 2g minus 2g cos theta. And a quick check that you can have when you do this problem is all my g's are going to cancel, right? That's a theta, that's obviously not going to cancel. All my g's cancel. So if you made a mistake anywhere in this problem and you had like a straight m here, right? But none of these other terms had an m, then at that point, you've realized that something's a bit off. And that's kind of a good trick to basically do when you finish a problem. See what units the answer is going to have. So if the problem asks for a speed, if my final solution doesn't have the dimension, like doesn't have the units of a speed, like if I get, I don't know, if I get my speed to be like AR, right? Acceleration times the radius, that's not going to have the right dimensions. So then I know my answer is definitely wrong. Anyways, simply solving this equation, I get that cos theta is equal to 2 over 3. So theta is equal to cos. So the -1, 2 over 3. So that's the solution to the question. Let me just check the chat if that made sense to everyone. I can't, I'm just trying to.
You've got nothing in the chats, but
Okay.
you do have a question in the Q&A, which says, could we do this problem by setting the conditions such that the resultant force towards the center doesn't meet required centripetal force?
I mean, that's kind of what, I mean, that seems like quite a complicated way to think of it, because like, remember that's you need to consider like whatever what this person asked in Q&A, whatever you did, you do have to have the natural reaction force somewhere. So if I'm understanding you correctly, and correct me if I'm wrong, if you were trying to see if the resultant force is not equal to the centripetal force, that's a bit of a, in my opinion anyways, I would kind of struggle to put that mathematically. I'm not really sure how that would work. So I think this is just the easiest way to do it. But if you get the right answer and you explain your work, then of course, that's obviously completely fine to do that way. Right. Oh, there we go. Okay. Because my chat button disappeared. That's why I couldn't access it. Okay. Right.
Don't worry, we've got a few more popping up in the Q&A as well. Are you able to see Q&A? I don't know how tiny a screen you're working on today.
No, I'm trying to, because I can just see the chat on my, I can just, because I'm sharing my iPad screen, so I can just see the chat.
I was
I
exactly
can
the
answer the
same when I
Q&A.
was on one. So
Yeah,
we've
I can just
got,
answer the Q&A session after I'm done with the question, because you can reply to that by typing, right?
yeah, you've got, how did you get the mg cos theta for the
Oh,
change in height? And couldn't we
again,
equate
I can see the Q&A now. Okay, right.
Okay,
How
great.
did you get the mg cos theta for the change in height? So basically for the change in height, well, the change in height is going to be this distance that I'm highlighting in red right now. So I just use trigonometry. Oh yeah, sorry. So this is going to be r, remember, because the radius is the same everywhere. So this distance is going to be r. So what I have to then do is just use my trigonometry. So I have an angle, and that's the adjacent side, and that's the hypotenuse. So I have to just use CAH. Okay, next questions. Couldn't we equate the cost component of the weight to be equal to n? There's no that wouldn't be right, because remember here you have the centripetal force, which means that you, I mean, oh, maybe, I mean, yeah, okay, so yeah, you're right. So maybe I think what the question means, could we equate the cost component of the weight to be equal to n? Yeah, you can't equate that because you have a centripetal force here. The point is, in circular motion, there is a resultant force. The resultant force is pointing towards the center of the circle. So you can't just balance the cost component of the weight to the reaction force, because if you had that, well, then according to this formula, your velocity would be 0. You wouldn't be having any circular motion. The key to making sure that something doesn't leave and this kind of goes into the next question, why is n is equal to 0 when I guess the marble leaves? It's because well, when n is equal to 0, it's, consider it in a way like the only reason why you ever feel the ground on your feet is because it's pushing back upon you. If the ground wasn't pushing on you, for example, when you're in an environment with no gravity, you don't feel the ground because it's not pushing back on you. It's sort of, if you consider starting at the top, right? And you can feel stepping, you can feel that you're stepping on the ground, right? But suddenly, as you go further and further away, you'll feel that pressure kind of ease. Maybe some of you have before been in a car where you kind of go over a hill and you kind of get like a little whoop feeling in your belly. And that's basically the same idea, right? It's because your natural reaction force is reducing. And we experience the world by, touching it and interacting it. So if we have nothing pushing up towards us, that has to mean we're no longer interacting with that object. I mean, in mechanics, obviously things get more complicated, but yeah, so that's part A, and I'm going to move on to part B just because, again, we have lots of questions and I don't want to take up too much time. And I'll answer any other
Perfect.
Q&A
Thank you, Aggie.
questions in the chat after. So part B basically says, how far away from the base will the marble land? So I'll set up this problem because the essence of this problem is basically solving a Suvat equation. So let me kind of set it up and then kind of write down the answer. And if anyone has any questions about Suvat, I can answer them in the chat later. So again, same situation. We have the marble, and now we found. So we have found. What have we found? We found that it leaves at this angle theta that we've just worked out below. And then so we've got that, so we know exactly what angle it leaves at. Then we can also find exactly how far away from the base of from the kind of middle of the hemisphere it's going to leave, because like I mentioned before, this is r, and this is also theta using the kind of zangles or whatever you want to call them, which means that this distance here is going to be r sine theta. So we have exactly how far below from the floor it's starting. How far, I mean, the bottom distance is not really relevant until the end. And then finally, we know its velocity, right? So its velocity, because the marble is traveling along the sphere, which means at the point at which it's going to leave the sphere, its velocity is going to be parallel to the sphere, right? Because there's no reason for it not to be parallel to the sphere. Which means that basically now I have my, my velocity, which I can work out through the formulas that I have above that I'll do it in a second. I have my theta, so my angle theta, if I just kind of, it takes a bit of thinking to kind of make sure that you're getting the right angle. So if I draw my V and kind of draw a triangle here, I know that this angle has to be 90 degrees because a radius and a tangent are perpendicular, which means that this is going to be 90 minus theta. And because I just drew a right angle triangle, this is going to be just theta. Right? Okay, so let's kind of sum up what we have. We have a velocity that the marble is going to leave at. We have the height at which it's going to leave the marble at. That's basically everything we need to solve a Suvat equation, to find exactly how far the marble is going to travel from this particular point that it leaves, let's call this D, until it lands at the bottom. So how do we do that? Let me just kind of quickly go through that, because this is at this point a Suvat problem. So let's kind of consider what the problem looks like vertically. So resolving vertically, what we have is okay, so I'm going to use S for the displacement, U for the initial velocity, V for the final velocity, A for the acceleration, and T for the time. So my displacement is going to be, well, let's say that this is positive and this is negative. It's going to be minus R cos theta. My initial velocity in the vertical direction is going to be minus V, and I believe that's going to be sine theta. Yes, that's going to be a sine theta. My final velocity, I don't care about. My acceleration is going to be minus G, because it's just the gravity, because it's now left, it's now left the hemisphere. And the time I'm just going to call T. Right, so that's how that is going to work. Let me just kind of yeah, okay. So yes, so basically you have this expression, and then what Suvat equation has, S, U, A, and T. Well, that's S is equal to UT plus a half AT squared. So what I'm going to do is basically I'll kind of trace it out again. And if anyone has any more questions, I'll go through it in the chat, right? So what I'm going to do is I'm going to firstly use the fact that cos theta is equal to 2/3. So sine theta is going to be equal to, so how do I find sine theta? Well, sine squared theta plus cos squared theta is equal to 1. So then I can say that sine squared theta plus 4/9 is equal to 1. So sine squared theta is equal to 5/9. So then my sine theta is going to be equal to root 5/9, like so. Yeah, I'm just checking if my maths is correct. Yeah. Right, okay, so I've got an expression for my sine theta, got an expression for my cos theta. So what I'm going to do is I'm just going to put everything that I've, just kind of wrote in my formula here. I'm going to write that minus R cos theta is equal to minus V sine theta T minus 1/2 GT squared. And then what I have to do now here is I'm going to insert cos theta, sine theta, and V, because remember from before, part A, I know that V squared over R is equal to, what did we get it to get? We got that to be V squared over R is equal to G cos theta. So that's what I do. I'm going to insert that into my formula above here. And then what I'm going to do is the formula is completely, absolutely horrible. So let me just kind of write it out, that the quadratic that you get after doing this and simplifying. I get G/2 T squared plus the square root of 10 g r over 27 t minus 2 over 3 r is equal to 0, then what you do is you solve the quadratic. Is it not 5 over root 9? Yes, it is 5 over root 9, which is 3. Thank you very much. I made a mistake. Why is it u is equal to minus v sine theta? It's minus because I've defined the down direction to be negative and the up direction to be positive. Yeah, and then what was I going to say? Yeah, so anyways, you solve the quadratic equation and you get a horrible expression for t. The only way that you can solve this is by using the quadratic formula. There's not like a nice neat trick. So you get that t is equal to the square root of 2r over 27g minus root 5 plus minus root 23. And one of these solutions, one of these solutions is clearly negative. Time's not negative, so I'm going to pick the positive solution, right? So that's how I find my time. So just to kind of quickly sum up what I did is I wrote a Suvat equation. I used all the kind of symbols that I've defined before, substituted the expressions for them from part A and everything that I've talked about here. And I got this quadratic equation. I solved this quadratic equation, so now I have my t. So my second step is going to be just a very simple, because I have no acceleration in the horizontal direction. I know that d is going to be equal to the horizontal velocity, which by resolving the forces is going to be, so let's say vx times the time, which is equal to some cos theta times the time, cos theta v times the time. So my final step is going to use the fact that the distance traveled is equal to the horizontal velocity times the time. And once again, I substitute all my expressions for theta. I substitute all my I substitute all my what was I going to say? All my expressions for v and then my expression for d. So you can kind of see that it's getting really horrible. So I get an expression for d. And finally, the very final thing that I do is I need to remember that the question asks how far from the base of the marble how far from the base of the hemisphere does the marble land. So the distance that the question actually wants is going to be, oh sorry, no, the d that I meant was this. No, okay, that's right. So yeah, okay, I was correct. So yeah, so I find d, and then the question is asking for the distance from the base of the marble. So the question is actually asking for this distance, which is just equal to, so let's call this, I don't know, let's call this big D. So big D is equal to little d minus, well, here was this little distance here. There's going to be r minus r sine theta. This is going to be big D is equal to d minus r sine theta, right? So let me kind of put that down here. So I get the final distance is equal to the distance that we've just found minus r, what was it? R 1 minus sine theta. Like so. And then again, and for the purpose of time, I'm not going to kind of go through all the symbols and exactly how you substitute it in, because it is just grinding through the algebra. It's not a pretty question. You get that this distance is approximately 0.125 r. Again, that's kind of the question, and I'll answer the ones in the Q&A. Actually, yeah, okay, I'll answer the ones in the Q&A, and
I was just about to suggest, Aggie, why don't I'll put you on to answering any questions about question 1 in the chat. We'll get Haron online to do question 2, and hopefully we'll get through all 8 questions. And if anyone misses a little bit, they can always watch the recording again to catch up
exactly,
as well. Perfect. In that case, hello, Aaron. It is over to you for question 2. Aggie now is going to man the chat
hi, everyone.
for any specific questions about question 1. And then obviously, Haron, after you're done with question 2, we'll switch over and you can man the chat while Aggie does question 3.
Yeah, I will do that. Yes, of course. Right, so let me share my screen. Sorry, I've turned on my camera just so, because I'm attending on the same device as I'm writing, and I don't think you guys want to see my chin, but hopefully we'll start in a second.
Yep,
can you guys
see your screen share?
my screen? Yeah, great. Yeah, sure. Let me just get a blank
there we are.
Page open. So
I'll stop my video so we've not got a weird double.
Yes, thank you.
Double cat situation going on.
Yes. Actually, if I can't delete that. It's yeah. So I'll be going through question 2. So this is the question that's asking about, consider a toy car going around a loop-de-loop. If the car is going too slowly, around the loop, at some point it will fall off. And I think this statement, can kind of use your intuition to think about what will happen in the real world if you have a toy car going around the loop. Yeah, so the first part of the question asks you if the car started at rest on a downwards ramp, which was initially at the same height as the loop, would the car make it around safely? So I think I can't draw a better diagram than the one that's given. I will try. So you have a loop you can just draw it as a circle, and the question is asking, if the I think you said the ball, yeah, a toy car, yeah. So if it starts at the same point, same height as the height of the loop, and I think will it make it around the loop? So I think this question is trying to get what this question is trying to get at is for you to use energy conservation. So if you think about at the start, the toy car is at rest, so all its energy is in its gravitational potential energy, it's GPE, and I'll just draw GPE here. And once the car, I keep on saying ball, sorry, the car rolls down to the bottom, all its we can treat this flat surface, the ground here, as GPE is equal to 0, and all its energy has gone to its kinetic energy. So I'll just label it as KE because I've said GPE before. So, and it's traveling around up to the top of the loop, and I think you can remember if you remember the formula for GPE is mgh. So as the car travels to the top, all its kinetic energy has been reconverted to the gravitational potential energy. So what I'm trying to say is that at the top of the loop, the car has a velocity of 0 because it has no kinetic energy. And I think this, if you struggle with this idea, that it's a bit easier if you just think about maybe something like a just a dip. And if you I think about, I don't know, skateboard park, and if a person were to skateboard from this side, he or she will they will end up on the other side. And that's basically energy conservation, all the gravitational potential energy going to kinetic and then going back to gravitational potential energy. So the first part of the question I haven't answered yet is talking about would the car make it around safely? And the answer to that is no, because if it has 0 velocity at the top of the loop, and it's kind of a similar concept as before, it will just fall down. And yeah, unfortunately, that toy car cannot make it around. Moving on to question part B. So Bob wants to find out, I won't read the question to save time, but I think the idea is that instead of downwards ramp, we have instead just a flat kind of lead up to the loop. And Bob wants to find out if it's possible to make it around the loop. So this idea is, again, just kind of concerning with circular motion. And I think the way to approach this would be to figure out what's the maximum speed that Bob needs at the bottom. I mean, actually, it's the minimum speed, I should say. What the question is asking, the minimum speed in miles per hour that Bob needs to drive at in order to perform the loop successfully. And I think to save a bit of time, I won't get into the numbers, and because miles per hour is it's not a very good unit to work with, instead of meters. So the idea that for this question would be to start I think I'll just label the bottom the speed, that's the minimum velocity at the speed. I think to make it a bit more clear, I'll label this as V min. And that's the minimum speed that Bob requires to get successfully gets over the loop. And the next part we need to concern ourselves with is what happens at the top of the loop. So just going back to the circular motion idea, what's there's a resultant force acting towards the center. So to make it around the loop, it has to the weight force downwards, that's the force that's providing the centripetal force, has to balance out with the centripetal force. And so the normal contact force would be 0 at the top, but that's not a worry because well, it's still going sideways, I think. Yeah. So this is the condition that we're set at. And well, the two m's should cancel. So you rearrange this equation to get V min. Actually, I think this it's a bit misleading that I've labeled V min here. But yeah, sorry. What I mean by V min is it would be the velocity of the speed of the car or speed of Bob at the top. The V min expression would be square root of RG. And once you get this, so kind of most of this mechanics problem is, you consider forces, consider energy, you have, two equations, and you can work out the quantities that you want to work out. So now consider, energy conservation. And for that, so consider, at the top, here, top of the loop, it has gravitational potential energy, and it also has the kinetic energy from its speed. And at the bottom, initially, before it goes onto the loop, it will have just the kinetic energy if we set the GP here as 0. So yeah, for the misleading speed that needs to be, and initial energy, like I said, is just the kinetic energy, and final energy is the kinetic energy plus this GPE. And I labeled H here, so H is just this height, and you can see because the loop is a circle, this H would be equal to 2R. So this V min here, we have this expression from here just to plug it in. So if we cancel out all the m's, V squared over 2. Actually, I can also multiply the whole thing by 2, so get rid of the fractions. V min squared is just RG plus 2G times H we got as 2R. So I think this should turn out, yeah, this gets me V naught squared is equal to 5GR. So V naught is root 5GR. And that is the speed that Bob requires to get over the loop, and specifies the minimum speed for, I think, the next part of the question. Yeah, and the numbers you just plug into the equation and convert to miles per hour, and not too concerned with that, just to save some time. So the final part of the question, he asked, is there any reason why Bob shouldn't go much faster than this minimum speed? So I think when I first saw this question, I said, yes, you can go a bit faster. But I think the key word here is much faster. So when it means much faster, when it says much faster in physics, it means it's, well, yeah, technically a lot larger. So kind of think about it's insanely large. So the answer to that would be no. And the main reason, I think, is because of the G forces or acceleration Bob experienced if he travels much faster than his minimum velocity V naught. So I think if I think for this question, I've thought of putting myself in Bob's car and then thinking, would I want to go on this loop-the-loop if I was traveling at a really fast speed? And yeah, I think I came up with the answer that no, because if you imagine this V naught as in something like, I don't know, like 100 V naught, for argument's sake, it's traveling a lot faster than what we worked out the minimum speed to be. And as the car travels around this loop, you can imagine kind of yourself getting flinged to the side due to the centrifugal force, actually. And if you want some kind of relationship with the some kind of mathematical expression, and you can remember this is just a rough estimate. It's not the exact way to work it out. But yeah, so this V squared term. So your force centripetal or centrifugal force experience is proportional V squared, and it will increase quite a lot. You will experience quite a large force, and that's, as you probably know, it's not very good for your body. A really high G force. So that would be my final answer for part C, and I will hand over to question
Thank you
3.
so much, Chiron. People are just popping
No problem.
questions in the Q&A for you, so you'll be able
Yeah,
to
I
answer
will answer
those.
that.
And because this is quite a big problem set, we're just going to jump straight into question 3 with Aggie. So over to you.
Okay, right. So yeah, I'll just answer the Q&A questions at the end. So don't feel like I'm ignoring you. Let me share my screen again, right? So it's going to take a. Oh no, it was actually very quickly. Right. So I've prepared these are the ingredients that I've prepared before. Anyways, but this is the diagram, and actually, let me say what the question is. So the question says a velodrome allows cyclists to travel at a high speed around tight corners since the track is banked at a steep angle. And I'm sure that given that the Olympics were just really recently, many of you have seen what a velodrome looks like. And the first part of the question asks, by drawing a force diagram, show why this banking is necessary. Determine an expression for the maximum speed a cyclist can travel at as a function of the radius r of the corner and the coefficient of the dynamical friction nu. So let's kind of answer the first part of the question, which asks by drawing. So exactly why do we need this whole thing to be banked? So let's consider the case if we didn't have a bank, right? We would have the natural reaction force here, and then we had just the mass mg. And clearly, because the cyclist is not flying over anywhere, in this case, n has to be equal to mg. And because the point is that in order to do circular motion around it, because a velodrome is circular by design, if you want to do circular motion, you have to have something supplying a centripetal force. And that centripetal force, clearly, if I didn't have any banking, it wouldn't not exist. And you might be thinking, well, why don't I have a friction here? You don't have a friction there because you're not moving that way. Like if there was no banking, you would not be prone to be, slipping downwards, right? As you are here, because in this case, clearly, gravity is going to push you downwards, right? But obviously that's not the case. That's not going to be the case here. Because, sorry, that's not going to be the case in the unbanked case because there's nothing to pull you down. So to kind of answer the question, we need the banking in order to have a source of centripetal force, right? Which is going to be both the friction and the gravity. Another reason, another question that you might be asking is, why did I draw the force? Why did I draw the friction to be here and not the friction to be pointing in the opposite direction? And that's because as I'm cycling around this velodrome, common experience, right? If you're like, I don't know if many of you have been on this ride where you like sit at the back and it rotates you, right? And you're like pushed into the back, right? I'm not going to go into detail why you're pushed, even though the centripetal force acts towards, right? But common sense, right? If you were just kind of if you were riding around the velodrome really, really, really quickly, which is what we're interested here, right? We're interested in maximum speeds, right? We're interested in, all these kind of really big kind of situations, which means that my friction should be kind of stopping me, because remember, friction always acts in the opposite direction to the one that you want to be moving. That's why my friction is going down, is because I want to be moving out. I want to leave the velodrome. That's the whole situation. Obviously, if that wasn't the case, then usually these signs get sorted out by themselves. But just to kind of keep this in mind, that if you have a velodrome and you have a limiting case like here, because we want a maximum speed, right? Like if we're slipping inside, clearly we're not going fast enough. Like clearly the limiting speed is going to be when we like getting pushed outside. Anyways, that's kind of why the banking is necessary. So now we want to find the maximum speed the cyclist can travel as a function of the radius around the corner and the coefficient of dynamical friction. Right, okay, so let's kind of resolve our forces. So we get that, again, we're not going to resolve them vertically and horizontally. We're going to resolve them perpendicular and parallel to the bank. So let's just kind of resolve it. So we get, if we resolve them perpendicular, so perp, I get that n cos theta minus f sine theta minus mg is equal to 0. Again, because this is perpendicular and there's no motion being perpendicular, the centripetal force, no, sorry, I'm not resolving them like this. I'm clearly resolving them like, yeah, I am actually resolving them this way because I forgot which way it acts. Anyways, so kind of resolving everything this way. Probably should label it a bit better like this. So horizontally and vertically, remember here, my centripetal force is going to act in this direction, right? So when I resolve everything vertically, as I did here, I have to have no resultant force because there's no vertical motion. Only the resultant force is the centripetal force horizontally, right? So let's kind of now resolve this horizontally. And again, kind of take, let me just kind of define my signs here, what I'm taking as positive and what I'm taking as negative, right? So when I do that, I get n plus n sine theta plus f cos theta is equal to mv squared over r. So let me kind of move this down. And I'm going to basically explain, no, ignore what I just said. So friction, as you probably know from your A-level maths courses, friction is given by the equation F is less than or equal to then the natural reaction force. I think F is the friction is less than or equal to the coefficient of friction times the natural reaction force. And you can stay in this inequality and do this entire question that I'm about to do in this inequality. And then you'll see that I'm going to get something of the form V is less than equal to, some value. So this value is going to be the maximum speed, as opposed to, V is less than, larger than some value, right? And then, you can kind of justify where it's a maximum speed and not a minimum speed. But for the purpose of being slick, I'm just going to basically consider the case, the case when I get a maximum speed. So F is equal to the coefficient of friction times the natural reaction force. Because again, I repeat, if you just use the general formula and then, ended up with some inequality that V is less than equal to some quantity, you can see that clearly this is going to be the maximum speed. But for simplicity, I'm just going to take that F is equal to I'm just going to take this equation. And again, if you want to work through it and confirm that it is a maximum speed and not a minimum speed, you're free to do that. Anyway, so I'm going to kind of put that into my formula above. So I get n cos theta minus nu n sine theta minus mg is equal to 0. So I get that n is equal to mg over cos theta minus mu sine theta. Right, okay, good. So kind of moving on. So I've got this formula 1 and I've got this formula 2 that I should also put my formula in the bottom. So I get n sine theta plus mu and cos theta is equal to mv squared over r. All I did was just substitute this into there and, factor at the end. So I get n sine theta plus mu cos theta is equal to mv squared over r, right? And that's going to be my equation 2. So what I'm going to do is I'm just going to simply substitute equation 1 into equation 2, and I get that mg, and then, it's quite long, so sine theta plus mu cos theta over cos theta minus mu sine theta, and then one big bracket is equal to mv squared over r. And then finally, just to kind of arrange it, because remember, we want the speed. So if I just rearrange this, I get that v is equal to the square root of sine theta plus mu cos theta gr over cos theta minus mu sine theta. And that's going to be my velocity, my maximum velocity. Again, if you just kind of did this whole question by saying that f is less than or equal to mu n, you'd get an inequality and you'd get something like v is less than or equal to this. So by default, this is going to be the maximum speed. So the next part of the question is just going to be, it's quite quick. So determine the value of mu required for the bike to travel at 80 kilometers an hour around corners of radius 25 meters with a maximum banking angle of 42 degrees. So I want mu, and I get that v is equal to 80 kilometers a second. R is equal to 25 meters and the angle is equal to 42 degrees. So what I need to do is I kind of need to rearrange the formula that I have above to get mu is equal to rather than v is equal to. So that's just kind of algebra that I'm not going to go through because there's no physics in it. You just have to rearrange this formula so that you get mu is equal to something. And I get that mu is equal to v squared cos theta minus gr sine theta over v squared sine theta plus gr cos theta. So what I'm going to do now is, I have this formula for mu, I have a value for v, I have a value for r, I have a value for theta, and I know that g is equal to 9.81 meters per second minus 1. I plug that all into here, and there's a caveat, and there's a little bit of a subtlety that I'm just going to discuss in a minute. I plug all these values here, and I get that mu is approximately equal to 0.40. So the kind of caveat that I wanted to mention is here I have meters per second minus 2, because it's an acceleration. Here, well, the angle doesn't matter, but here I have kilometers an hour, right? Clearly, one of these things is not like the other, which means that before I kind of do this whole calculation, I need to remember to convert my speed, to meters per second, right? Once I've converted my speed, it's literally just putting the numbers into the formula, right? So I rearrange the formula and I put numbers into it. And that's basically a wrap on that question. So I'll go and answer the ones in the Q&A now.
Fantastic. Thank you. I think you've just got one about the unbanked situations. I think you're good to go. Haron, over to you for question 4, I do believe.
Can you see my screen right now? I think
I
I've shared
can.
it.
That was seamless. Excellent. Love it.
Sure, yeah. I have one last question to answer. It's yeah, so question 10 is about the racing cars have spoilers which direct the airflow over the car upwards. Okay. And part A says asks to explain why this makes the car heavier with reference to at least one of Newton's laws of motions. Well, I mean, there's 3, so should probability-wise you're fine. So the spoilers, what they do is, well, the question gives it to you. It directs the flow over the car upwards. So I think if I just draw a simple Formula One car, just to as best as I can draw that. So when it directs the airflow upwards, what the question hints at when it says the Newton's laws of motion is that the air would also push the car down, and that's the every reaction has equal and opposite reaction, Newton's third law. So I'll repeat it a bit slower again. So the spoiler, that's the kind of like the fan thing at the back. It directs the air upwards, and so you can think of it as it's pushing air upwards. So the air is also exerting an equal and opposite force. That's air is pushing down on the car, so its effective weight increases. So that's what it. I mean, obviously, there's a lot of ambiguity about mass and weight in physics, but what it means by heavy is that it weighs more. And yeah, I'll move on to part B because we don't have much time. A student suggests that this is a silly design feature, as the heavier an object is, the slower it will go. What is the physics behind this argument, and is it correct? Yes. So I mean, this is a classic, I think, mistake when someone confuses mass and weight. So you can think just use your common sense, just that when the spoiler pushes air upwards, it's not exactly adding mass to the car. So the mass stays the same. So the mass of the car stays the same as you expect, but its weight increases. And because of what we just talked about in part A, you know, the air exerts a force down on the car. And about the heavier an object is, the slower it will go. And well, that is so Formula One cars are often concerned with more concerned with acceleration. So because we've said I've said before that the mass stays the same, so this mass m term stays the same. So well, the force provided by the Formula One car shouldn't change because it just has the engine. So this one is the constant, and this is also a constant. So this acceleration that the car is able to provide shouldn't change based on if you have the spoilers on or not. So, and a silly car design feature, I think it might go into that in a bit, but it's not a silly design feature, otherwise they want to have it. It's to increase the if you increase the weights downwards, you would have if you remember the equation for the friction on the car, is F equals to mu, and mu is the coefficient of friction. And this N here is the reaction force upwards. And if you increase the weight force downwards on the car, it will also increase the reaction force, that's the normal force, acting upwards. So if the normal force increases, the frictional force, F mu, will also increase. So this helps when the Formula One car goes around corners, when it goes around corners, because it needs it's traveling at the fastest speed it can go around the corner, so it needs as much friction as it can get, and that really helps them to bank around the corner. When I say bank, it's not exactly on a stunted gradient, but it helps the Formula One cars to corner, and well, go faster is what they want. So part C assume that again I won't read this part. So downforce created from the spoilers is proportional to v squared. I think that's reference to air resistance, because air resistance is proportional to v squared at high speeds. And if it is possible for racing car mass 800 kilograms to drive on the roof of a tunnel, so I think for this one I I'll just draw the cross section kind of, but of the tunnel. But in reality, the tunnel would be really really long, and the car would be traveling along the tunnel and slowly creeping its way upwards to achieve that 360 kind of turn. If it's possible for a racing car mass 800 kilograms to drive on the roof of a tunnel, provided it is traveling faster than 100 miles per hour, so that 100 miles per hour is sort of like the minimum velocity that we talked about before, you need to travel in a circular path and determine the value of the constant of proportionality. Okay, so again, I won't concern myself with the numbers, so I'll just label this 150 miles per hour the V min. So let's say the force that's force due to the air resistance, due to the air, I'll label this FA, is proportional to K. It's proportional to V squared, and you want the constant of so let's say the constant of proportionality is K. So this would mean FA is K V squared. So I mean, this is coming from FA is proportional to V squared and choosing that constant of proportionality being K. Yeah, so it's kind of similar to what we did before. And I think I can explain this in a chat, in a Q&A, if you guys have any questions after this. So you need to equate the weight force downwards to the air resistance that's pushing it down. And it doesn't help that the air that's caused by the swirl is pushing it down is also kind of downforce. So rearranging this equation, you'll get K is equal to mg over v squared, and sub in the values to get your K, and that should answer your question. And I'll move on. I'll stop sharing my screen and answer any questions.
Thank you. I think you've got 3 questions relating to question 4 and 1 left over from question 2.
Oh,
so
okay.
all
I forgot
good
to answer that one. Yeah, I'll answer that one once I've done with that. Okay, right. So this question is, I think, a really hard question, and I'm going to explain it in a way that, in my opinion, after kind of teaching this question for the 3rd year in a row, I honestly think that you just have to know what this kind of force that I'm going to talk about is. I mean, there's a whole argument in the solutions how you can derive it, but the solutions are wrong. The solutions that I have, I disagree with the answer that they give, because I'll show why the solutions are wrong as well, because there's a common misconception that I actually made when I was doing a course which talked about these forces. So so the way that I'm going to talk about it is, you do need this extra information, but I'm afraid that's the only way that I can explain it, because well, anyways, I'll just get on with it, and if it doesn't make sense, I'll talk to everyone. So the question basically asks, in Hertford, Hampshire, and Hertford, so just in UK, I guess, hurricanes hardly happen. However, if they were ever to happen, would they likely rotate clockwise, anti-clockwise, or have no preference? So the reason why hurricanes rotate is this force called the centripetal, the Coriolis force, sorry. The reason why hurricanes rotate is this effect called the Coriolis force. And I can kind of sit here for the next 15 minutes explaining you exactly why the Coriolis force comes from, and conservation of angular momentum, but that would not be a great use of my time, because there are many brilliant videos that exist on the Coriolis force, exactly how you get the equation for it, where it comes from, that you can just find on YouTube by Googling the Coriolis force. So what I'm going to do is I'm going to take the take the equation for the Coriolis force as given, right? And I'm just going to explain the symbols inside it. So the Coriolis force is a force that you experience when you rotate around something, just like you have the centripetal force. It's just another kind of type of force that we work with. So this is kind of the equation for it. So the Coriolis force is equal to the angular velocity, and I'll explain what that is in a minute, times the velocity. And here I'm using the vector product that you probably should be familiar with, but I think people should be familiar with the vector product. I don't know, maybe if not, someone can kind of I think it is part of the maths syllabus, but I'm not sure if it could be further maths. Anyways, if someone's not familiar with the vector product, then I'll try to explain it. Just put a question in the Q&A and I'll try to explain it without the vector product. But the vector product basically means that if I have 2 vectors, A and B, when I do the vector product, use something called the right-hand rule. So the direction of this vector product of A times B is in the direction perpendicular to both A and B. It's either pointing up or down, depending if it's A times B or B times A, right? This is just kind of a little introduction to the vector product. Again, if you're not familiar with it, then do put it in the Q&A, and I will try and answer that without the vector product later, right? So the property of the vector product, just to kind of simplify everything, is if I twist the vectors together, I get a minus. So I can rewrite this as v times the angular frequency and the angular velocity. So the angular velocity is something really easy to understand. Just like velocity is velocity, speed in a given direction. Angular velocity basically is that you point your thumb in the direction where the thing that an object is rotating around, right? And then the way that your fingers curl are the way that the object is rotating, because obviously an object can go anti-clockwise or clockwise, right? So if you just point your thumb, if here I have the Earth. So if I point my finger going upwards and I look down, that means that my Earth is turning around this axis in the anti-clockwise direction, right? So my Earth here is going to turn like so, right? So I've got two vectors. And exactly why do these hurricanes turn? So let's kind of consider just a mass of air moving upwards, right? So if I have a mass of air moving upwards, this is going to be the front view. So this is the front view, I guess, just, top, yeah, front view. And this is going to be the side view, because remember, the Earth is curved, right? So here I've got some kind of air traveling upwards, right? And if I just do a side view of it, it's going to be, add some sort of angle because it's parallel to the Earth. It's not leaving the Earth, right? That's why I drew a front view and a side view, so you can kind of know that this curvature is a thing that exists, right? So once I apply my vector product to my velocity, which I'm going to write here as v, once I apply my vector product here, I'm going to basically get that. So let's kind of put your finger in the direction of the velocity, put your finger in the direction of the angular velocity, and I get that the Coriolis force is going to be pointing in a direction going into the page. So again, kind of go back to my front view, the Coriolis force is going to be pointing in this direction, just using the properties of the vector product, right? This is a really, really hard question, and it does require a lot of knowledge. So as long as you kind of understand the general idea, I'm be more than happy with that, right? So that's what happens to air moving upwards, right? If I have air moving downwards, well, again, kind of let's do the side view. If I do the exact same calculation, I find that the Coriolis force is actually going out of the page. So back to my front view, I get that my Coriolis force is going to be pointing in this direction. So you can sort of see, because I just considered air going from, up and down, but obviously in a hurricane, you've got air coming from all directions. You can sort of see that if I had some sort of circle of particles here, well, these particles are going to be sent right. These particles are going to be sent, left. These particles are going to be sent right. So you can see that here my hurricanes are going to turn anti-clockwise, right? That's why, in the northern hemisphere, my hurricanes turn anti-clockwise. So what's a really easy mistake to make here? So you might kind of work this out and, just do this initial calculation right here and think, okay, well, they're clearly going to turn, clockwise because my Coriolis force is pointing in this direction. And I think that's where like the solutions got the wrong idea from, because I made this mistake until I actually sat the course. So yeah, that's basically how the Coriolis force works. You need to consider the direction of the air from all directions, right? So that's the northern hemisphere. Let's have a look at the southern hemisphere. So again, exactly the same kind of principles. I'm just going to, do it at the bottom of the Earth. Let's say that I have some air moving downwards, right? And I have some air moving upwards, right? So go to my amazing side view, and I get that then my air going downwards looks something like this, and my air moving upwards looks something like this, which means that now if I do my, whole calculation, I get that my Coriolis force is going to be pointing out of the page here and into the page here. So if I go to my front view, the Coriolis force is going to be pointing in this direction and then in this direction. So that's right. That's correct, right? So if I had kind of this circle of particles as you usually have in a hurricane, you can clearly see that that is going to turn clockwise, right? Because again, that's just, you can sort of imagine, I've just considered the kind of two extremes, so, the one's going from up and the one's going from down. But yeah, so then you can see that in the southern hemisphere, a hurricane would rotate clockwise. So again, to kind of highlight, just to quickly summarize this question, the Coriolis force is a force that objects have when they are when they are inside like something that rotates, right? Like the Earth. The Earth clearly rotates, right? The Coriolis force is a very special type of force that I've given an equation for here. It's expressed in terms of a vector product, which is basically a way that you multiply two vectors together. If you've done, I think it's A-level further maths actually, very sort of A-level further maths that they introduce it. So this is how you express the force. By considering just the movement of air upwards and downwards, I can intuit exactly which way it's going to be rotating. And again, very kind of key point is to know that you have to consider all the direction, not just one direction, because then you kind of come up with a mistake. And again, there's plenty of videos to watch about the Coriolis force. This is just for the purpose of trying keeping it brief. But you can go Google it, and there are much better explanations than I can provide within the time frame. So I'll answer any questions in the Q&A.
Thank you so much, Aggie. And I've seen you do this a few times. And I think the conclusion you and I have always come to is that this is a really interesting question. And it's lovely
It was
for
really
us to have a
hard.
chat about. But nobody should get too fussed about it. Like it's
Yeah,
not a
exactly.
big deal. So I've just popped in chat that anyone who hasn't seen the vector product has probably done force, current, and motion on a motor rule. And that's just the first example of vector product you do, but you're not told that it's a vector product. So that's the position I've left you in. But honestly, guys, don't worry too much about this one. It's a hard question. It's an interesting question, but don't worry too much about it.
It's a party trick. You can tell anyone. It's an interesting fact.
Pyron, over to you for our next question, which is a bit less strange than the Coriolis effect one.
Yeah, I feel like I'm getting the easier questions. Not a complaint. Yeah, so question 12 sorry, not the question 12. It'll be a different number to you. It's about the simple harmonic motion, and so we're moving on from circular motion. Is what I should bring up. So he asked you, it is possible to express its velocity as a function of time. Let me go back to my screen, and I don't think I need to draw too many things for this. As it is simply the time derivative of its displacement. Yeah, so I think guys probably are familiar with this idea that the velocity is the rate of change of displacement. Show that an object undergoing simple harmonic motion has a velocity as a function of displacement. It's given by v equals to this expression. So these questions that when they give you answer and ask you to show that, it's what everyone finds is that they're a bit easier because you know the answer, but it's the problem is getting there. So so for this one, I think I remember deriving this in A-level physics, but some of you might have not. So I think it's the starting point will be this equation here that stating that velocity of the rate of change of displacement. So if you have displacement that's x, I'll draw brackets t to show that it depends on t. And if you remember, I think this is just you can derive from the Newton's the force equation is given by the expression a cos omega t, and the a here is the amplitude. I hope you guys are familiar with this. The omega is the angular frequency. I'm not going to go too deep into this. So differentiation wise, this is just a mathematical procedure to work out the velocity. So if you differentiate this x displacement, you would get minus omega a sine omega t. So now you have to tell expression for the displacement and the velocity. And if you look at the expression here, the expression that we're trying to show, it has velocity, it has displacement, and it has angular frequency and amplitude. So basically, I'm trying to say that all the information we need are in these two equations here we've derived. So the best way to rearrange to get rid of the sines and cos because they don't appear in our final expression is to remember that I forgot what this is called, but this theorem that the cos squared x plus sine squared x is equal to 1. So rearranging, so I think the way I like to think about this is instead of trying to work with square roots, so like moving sine squared x to the other side and square rooting the whole thing, is to square these expressions. So you get, I'll omit the brackets t just to make it a bit more clear. X squared is given by a squared cos squared omega t, and v squared will be given by omega squared a squared sine squared omega t. And notice how this minus sign has gone because we've squared it, and it'll come back later. It's an interesting problem. So I mean, I think you might have heard is that squaring, you lose this information about the equation, but we'll gain it, we'll get it back after we've derived this. So we can, go whichever way you would like, but I think I prefer to change cos into sine. So cos squared x is equal to one minus sine squared x, and well, this x here I've written in quotes just to show you this. I've quoted an equation. This x we can just change to omega t. So what I'm trying to say is that x squared can be expressed as a squared 1 minus sine squared omega t. And yeah, this is just going through algebra. X squared is equals to a squared 1 minus. So this sine squared omega t we can replace by moving omega squared a squared over to the left-hand side. So this expression will get you v squared omega squared a squared. And I think we're most of the way there. And I think it will help if I move. We want the final expression in terms of v. So we want to get rid of everything that's, we want to get rid of these terms. And so let's just hope you can see that if I move this a squared to this left-hand side, x squared over a squared is equal to 1 minus v squared over omega squared a squared. And I think there's probably better ways to do this than we're doing right now. But so times everything by omega squared a squared just to get your v squared term, and rearranging this different sides, you get omega squared a squared minus omega squared x squared. I think, yeah, that is the expression. So you want to get the expression in terms of v, so you square root the whole thing. Omega squared, and I'll group the a squared minus x squared into brackets. Hopefully you can see why, because they both share the omega squared term. And the important point when I said earlier, you're losing information, is once you square root something, you'll get a plus or minus, because if you have the minus square roots, you square it, you also get the positive value. So this is, we're basically gaining the information about this minus sign earlier back. Kind of, you can think of it like that. And you can simplify it a bit further if you move this omega squared out of the square root and get your final expression. Yeah, and that is it for me.
Fantastic. Thank you so much.
And yeah, I'll go back to answering the questions.
Thank you. I think you've just got one, so that will keep you occupied. Aggie, over to you.
Yep, just
This is
sharing
seamless this evening. We're doing so well.
Literally, it's something's gonna happen now. You said that. All right, okay, so this is another question, and maybe Kat can correct me if I'm wrong, but I don't see a way in you can do this question without any prior information at the level of A-level physics. Anyways, so what was I saying?
I think this is
yeah.
the point where we're training beyond the PATS and A level, so that the PATS itself is less hard, isn't it?
I forgot to show this. I just wanted to show that for the previous question, that like, yes, this is what it looks like. Anyways, so continuing on to this question, it says, imagine that a tunnel is constructed straight through the center of the earth. If a person were to fall into the tunnel, would they arrive at the other end, describe the motion of the person, and either explain why the person would not reach the other end, or calculate the time taken for the person to travel from one end to the earth to another? So I'm just going to quickly kind of go through facts that you can deduce without any extra physics, right? So if I have an earth, right, and let's say that the tunnel is really, really thin, right, because we don't want to kind of change any of the main physics, right? So if I just sort of make this tunnel, and it's going to be a really, really thin tunnel, right? So kind of using our common sense, right? If I was right at the top, if I'm right at the top of this earth, I'm clearly going to feel a force pulling me down, right? That's just gravity, right? If I'm here, right, at this side of the earth, I'm also going to feel a force pushing me down, right? And remember that gravity is only attractive, and gravity between two objects is governed by Newton's law. So F is equal to m1 m2 over r squared, where m is the mass of one object, m1 is the mass of one object, m2 is the mass of another object, and r is just the distance between the two objects. So you can sort of think about it, right? If I was in the middle of the Earth, then my mass would be attracted by all the parts of, like, it's going to be attracted by all this kind of Earth around me, right? But because I'm saying that my tunnel is really, really, really thin, clearly that's just going to be completely symmetrical, right? I'm going to be pulled in the same direction everywhere. So it's reasonable to assume that that if I was right in the middle here, my force would just be zero. The force on me would just be zero, right? So what I'm saying is I have some sort of, let's call this I don't know, let's just call this F is equal to, like, I don't know, little f, just to kind of not overuse symbols. Here we also have this F equal to this little f, and in the middle, if I was in the middle of the Earth, I wouldn't feel anything, right? Because I'm just being pulled exactly the same everywhere. And now you might be thinking, okay, well, what does the force look like in the inside? Well, nature doesn't like gradients, right? Nature likes things to be smooth. So it's kind of reasonable to think that as I approach the center, the force that I feel is going to be downwards and it's going to be decreasing, right? So, here, if I kind of, use the length of the vectors to represent the strength of the force, I'd kind of expect the force to be smaller and smaller and smaller and smaller. And same thing here, right? Smaller and smaller and smaller and smaller. So this is kind of starting to look very similar to a situation that we already have looked at in physics, which is simple harmonic motion, because I have a force where the force is maximum at the two extremes of my motion, and it's zero right at the midpoint. So it's not a stupid kind of idea. Well, no idea zero is stupid. To think that this is going to be an example of simple harmonic motion. So again, if I was doing this question when I was 18 years old, back in the day, this is probably kind of how I would get as however many marks if I was the unfortunate soul on which this question got put on the pat, right? I'd sort of kind of maybe intuit why it's simple harmonic motion, and that's everything that I could personally do. But given that this is in this webinar, we kind of have the time to go through this whole question, I'll kind of go through it exactly exactly kind of derive the simple harmonic motion and why it is exactly simple harmonic motion. So because of this thing, and again, if you want to research it, you're free to go and have a browse on the internet, because of this thing called Gauss's law, which I'm not going to derive here, right? Gauss's law. It's going to be that the force that I feel, so F, the force that I feel when I'm inside an object is going to be MER times the mass of the person over r squared. And what's MER? So ME, if I'm here and I'm, let's kind of clear this just to give ourselves a bit more room. Oops, I cleared the entire Earth. So if I was here, right, and this is just my distance r from the center, the ME is going to be the mass contained in the sphere of radius r, which is below me, right? Again, if you want to know exactly where this law comes from, you can kind of be free to Google Gauss's law. It's because it's the same idea in electromagnetism. Again, I'm not going to go through it all, but you kind of have to take my word for it that when I'm inside an object, or I don't even have to be inside the object, if everything is very symmetrical, everything is spherical, there's no kind of wild spikes anywhere, the force that I'm going to feel is only going to be due to the mass that this kind of sphere below me is, the mass of the sphere below me. So that's how I get this expression, because this is just the regular Newton's law. It's just how exactly am I finding my other mass, and that's kind of what I'm telling you. That's what I'm telling you, is that this mass is going to be the mass enclosed by a sphere of radius r. Right, so now I have this expression, I can kind of do the question, right? So clearly ME is just going to be 4 over 3 pi r cubed, where rho times the density, where just the rho is the density of the Earth. Density of the Earth. And we can easily work out rho, because rho is just equal to the mass over volume. So it's going to be the mass of the Earth, which I'm just going to call ME, over 4 over 3 pi RE cubed, where RE is just the radius of the Earth, right? Good. So I have this expression, and MP is just my mass, right? So I plug this into my force. So I get that the force is equal to G times 4 over 3 pi R cubed times the density times NP times 1 over R squared. So let's kind of tidy this up. So I get that the force is equal to 4g over 3 pi times rho times mp times just r, because here I have an r cubed and here I have 1 over r squared. Let me just put my density just to, you know, make the whole expression a bit more, look a bit more nicer. Once I put the expression for the density into my formula here, I get that the force is equal to GME mp r over re cubed. So that's the force that I'm going to feel if I'm inside the Earth, a distance r from its center. That is the force that I'm going to feel. And that force is going to be, again, just acting towards the center, the way that you're used to with gravitational fields. Good. So that's our expression for the force. But also, of course, force is just equal to the mass times the acceleration, right? That's just Newton's law. So the direction of the force, just to kind of, you know, if I equate these two equations here, I get that MPA is equal to minus, and I'm going to say why I have the minus here, GME MPR over RE cubed. So the way that I define my acceleration here, my R coordinate is increasing away from the Earth, right? So this is away from the Earth is the positive direction, right? Which means that my acceleration, again, if I want to kind of label everything in terms of positive and negative, if my distances are, you know, if away from the Earth is positive, then because my force is acting towards the Earth, that's why it's going to be negative. Good. So that's, you know, again, to kind of recap how I got this expression, the minus is, so the left-hand side is just Newton's law. The right-hand side is something that you have to know this kind of Gauss's theorem to derive. And the minus comes from the fact that my force is going to be acting, you know, towards the Earth, but I've defined my coordinate to be away from the Earth. And now I can just divide by MP, and I get that A is equal to minus GME over RE cubed times R. So I'm sure that many of you have seen the kind of equation that just completely governs circular motion, right? In terms of circular motion, the acceleration is equal to minus omega squared x. So you can see that, you know, equation 1 and equation 2 are exactly the same as long as omega squared is equal to, you know, GME over RE cubed. So my motion has to be circular, has to be simple harmonic motion, because the equation has the form of a simple harmonic motion equation. Therefore, my motion is simple harmonic motion. All right. So what would happen is if you fell in, you'd kind of go like this, and then, you know, you'd fall in, then you'd jump back the other end, and then you just keep, you know, oscillating until you decided to jump out. So I can find my frequency, and that's just the square root of GME over RE cubed. So now we've described the motion of the Earth. The final thing that we have to do is to just see, well, how long is it going to take me to go from one end to the other? And you might be thinking, oh, wait, so let's kind of work what that time is. So again, using kind of the formulas that you're familiar with, simple harmonic motion, either that omega is equal to 2 pi times the frequency, and the frequency is equal to 1 over the time period. So I get that omega is equal to 2 pi over the time period. So the time period of the motion is equal to 2 pi over omega, which is equal to 2 pi times RE cubed over GME, like so. So now what's the time for me to go from the top of my tunnel to the bottom of my tunnel? Well, remember that this time in simple harmonic motion, if I just have like a bob on a spring, this time period is the time that it takes for you to go from one extreme all the way to the other extreme and back. And here my motion would go, you know, from one extreme to the bottom and back, which means that the time that I've just wrote down here, that's how long it's going to take me to go from the top of the Earth to the bottom of the Earth and then back to the top. But I only want the time that it takes for me to go from one into the other, which means that the time it takes for me to transverse the Earth would be 2 over 2. So time to fall through would be T over 2, which is equal to pi root RE cubed over GME. Yeah, so that's basically kind of that's basically how the question would go. And then, you know, you can plug in the standard constants for the radius of the Earth and the mass of the Earth to get, you know, how long it would take, and it would take around 85 minutes to kind of go through it. And right, so I'll kind of just answer the questions in the Q&A, because I know this is quite a difficult that's quite
Amazing.
a difficult
No,
question.
we're good, but we're gonna get Hiron on straight away to see if we can finish question 8, which we almost never get to. So Hiron, over to you.
Right. Okay. I guess I'll speed through this question.
No pressure, don't worry.
And
Just do what you need
yeah,
to do.
so this is about the film Hannibal, and the situation is, you have a tank is falling onto the sky, and the main character Liam Neeson is firing the tank shells, sorry, to move the tank horizontally to change its momentum, whichever you want to think about this. So, and I'll just give you a quick answer. Yes, it will. And just if we don't finish in time, and the way you approach this is you're given in this nice kind of bullet point formats the velocity and time and mass. So when you think about velocity and if you're given velocity and mass, you should think about momentum, and you can work out the force exerted by firing the shells using the definition of force is the rate of change of a momentum, and like the hint said, you can kind of smooth out this kind of force. Well, in reality, the impulses will be kind of spikes and goes to zero. Sorry, it's not a very good diagram, but you can think of it as an average force, which is one of the assumptions that we can make. So the change in momentum of firing the shell is the mass of the shell, that's 10 kilograms, and times the velocity of the muzzle velocity, what it's called. So that's relative velocity of the shell to the tank once it was fired. And the change in time, we can assume that is just the time between shots is 3.5. And this is working out the number here. It should be 5,000 newtons. So this is kind of showing what's the average force. You scrap the idea of firing shells. If you just have a continuous force applying to the horizontally to the tank, what that force would be. And once you get a force, F equals ma, you can work out acceleration. And once you have acceleration, Suvat should solve the problem most of the time if the acceleration is constant, which in this case it is, because the force we've assumed is constant divided by mass. And this mass here is different from this 10 kilograms we worked out before of the muzzle velocity, because you're accelerating the entire tank, not just your shell. So the mass here is given by 22,000. Yeah, that's 22 ton. That's tank will weigh quite a lot. And the acceleration turns out to be 0.25 meters per second squared. So yeah, again, Suvat, the equation that will help the most here is S equals to UT plus a half AT squared. So you want to work out the horizontal distances traveled. So it's moving a trajectory like this, but actually it's not. This kind of shows you it's projectile motion, but it's not. So initial velocity is 0, so you can scrap this term, and you work out the time and the total time that's elapses, and you can work out that, and the acceleration from before, so you should work out the distance you can travel horizontally. And to work out my apologies. Let me go through this slightly slower. So half AT squared. So we actually don't know the time. We can't work out the time yet, but you know the acceleration and you know the distance to the lake. So you can rearrange this to get the time. Sorry about that. Which you get as 80 seconds. And then the next part is doing the Suvat vertically to show that you can, in fact, travel to the lake. And in fact, it does. And I won't go through that just because we've run out of time. But, just going through the whole question again, just once you get change of momentum, rate of change of momentum, you get force. Force leads to acceleration. And it's constant acceleration, you can use Suvat to solve the problem. And step by step, you get the answer. And that's it from me.
Fantastic. Thank you so much for that. I'm just
Sorry, I
switching
had to
my
speed
video
through the
back
last
on.
question.
No, it's all good. Don't worry. We quite often don't actually get to the end. So I will round up. Haron, you've got one question, if you don't mind answering that just before I end the webinar for everyone.
Yeah, I
Thank
would do
you
that.
so much to our presenters this evening. You guys have both been fantastic, and it's lovely to see your approach to solving problems. For everyone who is still on the call, I will share the recording of this and make it live tomorrow, so you can come back and look through it as you need to. We're going to answer a couple of questions in the Q&A just before we finish, and I will be ending the webinar at 8:05. Next week, webinar 7 is our final study focus session. We have a teacher who is joining us to take you through tricky problem solving. So we've kind of reached our full circle. I really hope to see you there, and I'll get the emails out to you tomorrow. So you can switch my camera off. Goodbye for now, everyone. We'll answer those couple of questions.